Hello students, today we will read about equipotential surfaces. In this topic we will read what is equipotential surface, how we aim at finding the potential on such surfaces, what are the application of these surfaces and how they are important. So let's start with the class by understanding first of all what do we mean by the equipotential surface. An equipotential surface is a surface with a constant value of potential at a point on the surface. For a single charge q, the potential is given by V equals to 1 by 4 pi epsilon naught into q by r. This is the potential for a given single charge. We have seen this in the previous section where we have defined the potential for a given system, potential for given charge. Now this shows that V is constant if R is constant. Here the changing factor in this whole equation V equals to 1 by 4 pi epsilon naught into Q upon R. The changing factor is only R. R is a factor which keep on changing. Why is not our Q changing? Because Q is same for all the distances, let it be R1, R2 till Rn, whatever the distance is, Q will remain same. We are defining the potential with respect to given charge, and then this particular value 1 by 4 pi epsilon naught is constant for everything. Like we have learned, this is a proportional constant and its value is given by 9 into 10 to the power 9 always and always. So the only thing which is variable is R, and hence our potential, it will increase or it will decrease, will depend upon the R. So the relation between our V and R is inversely proportional. V is inversely proportional to the distance. So in case of the distance increasing, our potential will keep decreasing. So as we are seeing in this particular diagram, in this diagram this is R1, R2, R3 and R4, and here it is V1, V2, V3, V4. In this case, if we see the trend followed is V1 greater than V2, V1 greater than V2, greater than V3 and greater than V4 and so on, because R1 is smaller than R2, is smaller than R3, is smaller than R4. So from here we understand that V is proportional to 1 by R. If V increases, R will decrease, or if R increases, V will decrease. I will write over here, if R decreases, V will increase, or vice versa. Now, thus equipotential surfaces of a single point charge are concentric. See in this, these are concentric, having the same center as of the Q charge. Spherical surfaces centered at the charge. Electric field lines for a single charge are radial lines starting from or ending at the charge, depending upon the whether Q is positive or negative. Similar for the electric field lines, we can see that for potential we give concentric circle. For we define concentric circles, and for our given electric field what we aim at defining is the radial lines. These lines will be radially outward or inward, outward or inward, and that depends upon the given charge. If charge is positive, electric field lines will be outward radially, and if charge is negative, electric field line will be inward with respect to the given charge. Now the electric field lines for a single charge at every point is normal to the equipotential surfaces passing through that point. These electric field lines are normal to these equipotential surfaces. For this we have read previously about the about these tangents, like these are the electric fields made around a charge, and for this particular position we define these tangents. These tangents gives us direction for our electric field lines. This is true in general for any charge configuration. Equipotential surfaces through a point is normal to the electric field at that point. So the last line says that electric field lines and voltage for equipotential surface are perpendicular to each other. How does that is happening? Like these are electric field, along this concentric field, the electric field, only on that the voltage will come and get superimposed, but the direction is given by these tangents, so we cannot do anything. So these tangents and this this potential V and these tangents are known, and they have shown the property of being perpendicular. Now proof to the above statement, whatever statements we have given, like the first one is that V equals to K Q upon R. Second one, V increases, R decreases, they are inversely proportional to each other. These are the things we have discussed so far, and we have read that these potential forms concentric circle, whereas the other doctor concentric circles in this. And the normal electric field is given by arrows. These arrows are outward for the positive charge, as you can see the figure over here, and are inward in case of negative charges. Now what are the proofs we are going to read is, if fields were not normal to the equipotential surfaces, it would have non-zero component along the surface. They will have a non-zero component along the surface. To move a unit test charge against the direction of the component of field, work would have to be done. Now the concept is equipotential surface and electric fields are not perpendicular to each other, not perpendicular to each other. In that case, there exists an electric field along the electric field along EPS. Now when this happens, we need to do work. We need to do work for any change or bringing the test charge in it. Our potential will lose its freedom in case they are not perpendicular. But this contradiction to the definition of an equipotential surface. Now this is a contradiction. How it is? There is no potential difference between any two points on the surface and no work is required to move a test charge from the surface. As we say, this concentric circle, this circle will have a single potential. Now this circle will have one more potential energy which is lesser than the above one but is different. This have another and this have another. Like all these colored concentric circles have different V value, and as we say, this on this particular surface, as the potential is same, what we can conclude is that to move a charge in this area, to move a charge in this area is the surface of the given concentric circle. Okay, there is no work is needed, no work needed, no work needed. But in case this is happening, then work is needed. So this is the contradiction. This is the contradiction, that equipotential surfaces have equal potential, so there should not be any work done for bringing any test charge. Okay, but this condition is satisfied by this condition also, that these two values should not be perpendicular. Now the electric field must therefore be normal to the equipotential surface at every point. Equipotential surfaces offers an alternatives visual picture in addition to the picture of electric field lines around a charged configuration. So like along a charged configuration, we have seen how the field lines and force lines behave. Force line behaves, but this gives us another 3D view which helps us to understand various other mechanisms in the physics. So see here, we got a square, or if you can see it as rectangle, anything, a quadrilateral, which I aim is a square, and here is the beam which is passing through these equipotential surfaces. As these all surfaces V1, V2 and V3 all are having same potential, so in this case what is happening, all these are having the same potential, so these lines, these electric field lines are uniform over here, uniform here, uniform for the plate number 2 and uniform for the plate number 3. Incoming is uniform, and here we can see the outgoing is also uniform. So in such case, these equipotential surfaces, have good like potential uniformly distributed, and hence uniform electric field lines, uniform electric field lines. Now for a uniform electric field E, for a uniform electric field E, say along the x-axis, the equipotential surfaces are planes normal to x-axis, that is plane parallel to yz plane. So what exactly is it? That we got our xyz plane. If we think this as x, this is y, and this is z, so anything which is parallel to this and have nothing to do with the x-axis, kind of a surprise over here, that these field lines are placed in such a manner. Why so? Because we aim at making these fields perpendicular to the voltage, and here we are not considering the curved fields, we are considering the tangential field which gives the direction. Okay, so these are plane parallels. Now we got some equipotential surfaces. In that we are looking at a dipole. This is having a negative charge and a positive charge, and both are having these potentials around themselves. Now at a point, this potential like from the negative it start growing up and it will aim at extending towards the positive. Similarly, from the positive also they will aim at extending towards the negative. In a dipole, the distance will be maintained at as per to the requirement, but along with the distance there will be force of attraction and successive repulsions also. Now the other one is this two identical positive charge. In case instead of positive we are having negative charge, what will happen? Same kind of diagram we will get. There is no such change in the positive or negative unless until both are the identical. Now both are identical, they are having this uh, concentric circles of voltage, concentric circles of our potential, and from here also potentials concentric circles are made, and these at a point here will show some sort of repulsion. This will not show, but this which are coming in contact will show the repulsion. Why does the repulsion? Because we have read basically that unlike charges attract each other and the like charges aim at repulsing each other. Now relation between a field and potential, this is very much important for us to understand what is the relation between field and potential. The only one thing which we are reading so far is that both are perpendicular, both are perpendicular to each other. Now see, consider two closely spaced equipotential surfaces A and B with the potential value V and V del V, where del V is the change in the V in the direction of electric field E. So see here, we are having one surface like this. This is our surface number 1. Okay, and below this or above this, anything we can take, but the difference of the volume which is seen between these two equipotential surfaces is denoted by del V, okay. So this is one surface and the other one is this. Other surface is this. Just a minute, for your convenience I am coloring it so that it is understood. I tried to make a proper diagram, but this shading will help you to understand which two particular surface we are talking. One is the blue one, other one is the grey one. Okay, so these are the two surfaces and the difference is of del V volume. Now let P be the point on the surface of B and del L be the perpendicular distance of the surface A from P. So this is the charge difference, and the particular value, the length, how much far apart these are, is given by del L. See, I have given over here in the diagram, it is given by del L. Now if a unit positive charge is moved along the perpendicular from surface B to surface A against the electric field, we are coming from our surface B to surface A like this, and this is perpendicular to the surface A, surface B, but is against electric field. This is against electric field. So the work done in such case, because we are going against the electric field, we aim at doing some work in bringing the test charge. So the work done is given by electric field into the distance between these two equipotential surfaces. Electric field into the distance between these two surfaces. Why we have taken a mode over here? Mode we take to discriminate or eliminate any negative value. Eliminate any negative value if it is not of very much importance. Now this work is equal to the potential difference also, like at a particular point there is one potential, at a other point there is another potential. So from bringing any object from this to this position will need some change in the potential, and that is given by V2 minus V1 or vice versa. Okay, now this work equals to the potential difference VA minus VB. Thus in the previous slide we have seen this equation equals to V minus V plus del V. So the volume of first equipotential surface, volume of surface 1 minus volume of surface 2, volume of surface 2. It should be seen in this way. So we will get E del L equals to minus del V. Now for E we will do some changes and we will get del V by del L. So this is the value for the electric field in terms of potential. Now one thing which we should understand is that electric field is given as kq upon r square, whereas potential is given as kq upon r. So both are basically same. In such a case, what exactly happens is that we do not understand how these two are related. So see over here, it is kq by r into 1 by r. So this is V. So V upon R. This is what we have derived. So here this is what we derived in the other words. This is in the terminologies of K and V. The general formula for the two we have used. Okay. Now since del V is negative, we will introduce modulus. This modulus will help us to retrieve the negative sign from the given equation. Now the above equation can be rewritten as E equals to del minus del V by del L equals to plus of del V by del L. Here we have taken mode. Okay, here we have taken mode. Arranging the two important conclusions concerning the relation between electric field and potential is: electric field is in direction in which the potential decreases steepest. Its magnitude is given by change in the magnitude of potential per unit displacement normal to the equipotential surfaces of the point. These two conclusions are from this equation: E equals to V upon L. So what basically is happening, E and V are proportional to each other. Any value increasing will increase the other value. Any component increasing, we will see other component increasing too. Okay, now the other relation which we find is E upon del L, that is inversely proportional. So in this case our E increases only when L decreases, or the given distance, length, or whatever it is, it gets decreased. Okay, these two things are concluded. So let's just go through these important conclusions once again. Electric field is in direction in which the potential decreases steepest. Electric field will always go in the direction where there is decreasing potential. So it will be easy for the electric field to be uniform. If it is like this potential and electric field are in the same flow, then it will be like this is the E, and the potential is also uniform over the given surface. So this E will remain uniform for a given surface, Now the second one is its magnitude is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at the point. Normal to the equipotential surface states that our V and E are perpendicular to each other, are normal. Like if this is the E, V will be given on this, like this. So this is already, we have proved one thing, that V and E are perpendicular. Now what it says is that the E's magnitude will change with the voltage, per unit displacement. So this is what they aim at saying. Our electric field is proportional to V by L, and that is written as potential per unit displacement. E is defined as potential per unit displacement. Okay, so hope you understand today's topic. It is basically based on the equipotential surfaces. Equipotential surfaces are the surfaces which are having the equal potential. We can see a concentric set of circles where each circle will have some potential. From circle to circle the potential will increase or decrease, but along that one circle the whole circumference will have the same potential. Then we aim at finding the relation of electric field to the potential, and we found that electric field is equal to potential per unit displacement. Then we get to know that this electric field and the given potential are perpendicular to each other. This perpendicular to each other is needed to maintain because this one will give us a uniform electric field distribution. So these are the important key points in this concept, and here we end our class about the equipotential surfaces, and in the next class we will deal with a new topic of the same chapter. Hope you understood this chapter very well, like this particular concept of equipotential surfaces very well, and you have understood how important it is to define electric field as well as potential for the given equipotential surface. So that's all for today's class. We'll meet in the next video lecture. Till the time, bye bye, have a good day.